If you've been learning about PN, you may have heard you need to exercise. Maybe you wonder why. Your focus may initially be on the uncomfortable sensations of PN, including numbness and, for many, pain. While pain is immediate and must be dealt with, for most of us, the greatest danger is falling. As our balance deteriorates, fall risk increases. But if PN damage or kills nerves, what does that have to do with our ability to move? We all know that exercise makes us stronger at any age, but what does that have to do with a disease that damages our nerves? This presentation is an attempt to make that connection clear. Please note that the most important source I'm using here is the textbook used to train coaches and trainers. With PN, personal trainers, physical therapists, and perhaps dance instructors or Zumba teachers become the most relevant medical specialists. That is especially true after neurologists have done all their tests and concluded that they cannot do anything further to help you. This may be the most important slide in this presentation. PN manifests in many ways. For most, it shows up first with discomfort, often a tingle in a toe, something that can be and often is ignored for way too long. For a substantial minority, it shows up with severe discomfort. But an alert and trained doctor can diagnose the presence of the kind of PN that affects balance and strength. We call that motor or sensory motor PN. Most PN cases are like that. Damage can be confirmed with special tests, including electromyography and nerve conduction tests. I want you to consider these three yes or no questions. Have you or someone you love been diagnosed with motor or sensory motor peripheral neuropathy? That is, was a test of your large sensory nerve, such as a nerve conduction test, positive, suggesting that the response to stimulus is abnormal? If so, you need to ask two additional questions. Second, are you having trouble, even minor trouble, with your balance? And third, is neuropathy the only known source of your balance issues? There might be other causes, of course. Let's look at some possible answers. If the first answer is yes, and the second is no, you may have caught this beast before disaster is inevitable. You really need to understand the lessons of this presentation and act on them. Exercise may be an off-ramp for you. For most of us, balance issues come on slowly. After diagnosis, years or perhaps decades can pass without incident. Following my toe tingle and immediate diagnosis, it was 13 years before my first out-of-the-blue balance wobble. I was totally surprised. My thoughts were, what the hell? As we will see, the brain can compensate for the loss of many nerves. Balance can seem fine, even when the loss of nerves is quite large. One may, for a long time, not see much loss of the ability to stand and walk. We have anecdotal reports of people whose progression seems to have stopped after they became gym rats. Unfortunately, at this point, the evidence is quite limited, since very few PN patients have ever been warned early and told to emphasize exercise. If all three answers are yes, then get a grip. Your wild ride has started. You've almost certainly already lost a major portion of the nerves in your legs. Disability is ready to come knocking. As I said, for most of us, balance issues progress slowly as the brain compensates for the loss of nerves. Balance can seem pretty good. After my first wobble at 13 years in, with lots of exercise, it was 8 more years before things got bad, and I started falling. At some point, the loss became too great, and the wobbles started to dominate. But I was no gym rat. Suppose only the first two answers are yes, where we have both PN and balance issues, but there's another reason for balance problems. In that case, it's hard to be certain about the future of balance progression. Of course, try to treat those other causes, but one should, while dealing with those other causes, act as if PN was the primary driver of the balance problems. Act for now as if all three answers are yes. If you've been diagnosed with autonomic or so-called small fiber PN and had a negative nerve conduction test, then the future is cloudy. Will it progress to trouble with balance? We're not sure. The evidence is hard to understand. The symptoms in such cases often include pain, changes in digestion, or other autonomic aspects such as sweat glands. Pain is very tricky. Unlike nerve conduction speed, which is straightforward to measure, pain is a complex product of that complicated, life-affected mess that we call our brain. Digestive symptoms, such as irritable bowel, can be equally complex to diagnose, since they are also affected by stress and emotions. Given this ambiguity, it's probably best to assume the worst and prepare for future balance problems with exercise. Exercise is good for many reasons other than fighting PN, including relieving stress. More colorfully, try acting as if you were standing on a railroad track and a freight train is coming right at you. Take some steps to get out of the way. Most, perhaps all, of the stuff one can find on the internet on PN will mention weakness and/or balance. It's rarely mentioned first or prominently. That's a terrible shame. PN can and probably will rob the patient of many years of full life. For some, severe issues with pain can start that robbery early. For the majority, the robbery comes later. But why? What is going on in the body to steal away balance, and with it, years of full life as we struggle with disability? To start, let me tell you what I'm going to tell you about PN and exercise. First, we need to preserve or build the muscles needed for balance. We lose muscles in two ways. Way one, when our nerves die, the muscle cells die. By the way, the muscle may not die, it may simply atrophy or turn into fat storage. Regardless, it will no longer function to help us move. Way two, our muscles are composed of types. The slower, weaker ones are essential for life. When those essential slow ones die, the body will compensate by converting some remaining faster, stronger ones into the slower, weaker ones, just to keep us alive. Unfortunately, that conversion weakens us. Exercise pushes the body to preserve the faster, stronger ones. It's an issue of use or lose. Second, as we lose sensory nerves, we rob the brain of the signals it uses to control our muscles. The brain can, and usually does, compensate for this loss of information, up to a point. Then its timing gets degraded, and as we'll see, timing is a key element in getting strength from our muscles. But our brain needs time to learn how to deal with this loss of sensory inputs. The brain needs time to learn. Exercise gives brain the opportunities it needs to learn. And all of this is on top of the benefits from exercise that you've always been told about. Muscles and movement. We must start somewhere. What do muscles do? They contract, they get shorter, and then they relax. They contract a little or a lot, but that's all they do. When they contract, they pull on something. In this presentation, we'll be talking mainly about skeletal muscles that pull on bones, but the same is basically true of the muscles that move your eyes, eyebrows, tongue, gut, and heart. PN can damage all of them. Let me show you about a skeletal muscle. A skeletal muscle is structured like a Russian doll with bits within bits. On the left of this diagram is the innermost part, the filaments. Filaments move, they squeeze together, they contract. As we will see, it takes energy, nerves, and exquisite timing to be effective. I'll demonstrate this as we go on. The filaments are bundled together for storage in muscle fibers. Muscle fibers are sometimes referred to as muscle cells, since each is a cell. Each fiber or cell is as long as the muscle it is part of. Some muscles have only a few fibers or cells. Some, like leg muscles, have thousands. Muscle fibers are grouped inside a muscle fiber bundle. The muscle fiber bundle is the key player. Most of this presentation will refer to bundles, not the individual muscle fiber cells. A set of bundles is found inside each muscle belly. The belly is what you feel when you touch an arm or a leg muscle. The belly, in turn, is connected to a tendon. Finally, as a payoff, the tendon pulls on a bone, and the bone might help us do something. Muscles are controlled by the signals from nerves called motor nerves. Note, in this presentation, I'll usually use the common word nerve rather than the technically accurate word neuron. Please forgive me for using the common word. I don't think it'll be confusing in this case. All the illustrations in this presentation point to objects that are, technically speaking, neurons. When doing more technically precise in an academic context, the word nerve is normally reserved for use when referring to a body part that holds a bundle of neurons, not a single neuron. For instance, you may have heard of the vagus nerve. Anyway, motor nerves or neurons usually start in the spinal column. A single motor nerve reaches out and touches and thus controls a single muscle fiber bundle. A single bundle contains many, perhaps hundreds, of muscle fiber cells. The end of the nerve branches out into individual fibers that touch each muscle fiber cell individually. So all the fibers in a bundle are told to contract at the same time. In short, each motor nerve controls one muscle bundle. All the fibers in that bundle are told to move at the same time. There are three types of muscle fibers called fast, medium, and slow. This drawing uses color to show that each muscle each muscle bundle specializes in one type. Red for slow, pink for medium, and white for fast. All fibers in a bundle, as I said, are the same type. An important term is the word twitch. A twitch is the process that happens when a nerve sends a signal to a muscle bundle, and the bundle responds by compressing slightly. The three types differ in several ways, including their twitch speed. Twitch speed is the time it takes for the response from the signal to reach its peak compression, that is, peak force or peak strength, and then relax and return to its relaxed state. The next slide will show that. Let me clarify some terminology here. The terms slow and fast are commonly used terms for these muscle types in the technical literature. Medium is not a common term. The technical terms are, respectively, type 1, type 2A, and type 2B. Personally, I think you will, a bit below, see that the word medium is a lot easier to understand than type 2B, that it precisely makes the point and will be much clearer to anyone who's not interested in learning technical terms. This slide shows what a single twitch does. The video takes a second or two to show what, in real time, is quite momentary. The previous slide showed that the innermost portion of a muscle is composed of filaments. The filaments, the big red structures in this video, are pulled closer together to create compression. The ends of the filaments that are not shown here are linked within that Russian doll-like structure of the muscle to transmit that compression motion to a tendon to move the bone. Energy stored in the muscle cell is used to make this movement. That energy comes directly or indirectly from the sugar, oxygen, and chemicals in your blood. They, in turn, come from the food we eat and the air we breathe. Let me show you this movement a few more times. In and out. In and out. Very slight motion. In and out. This slide is to emphasize that the term twitch speed refers to response time. A slow muscle responds to a signal by taking more time. Medium takes less time, and fast twitch muscles finish faster still. So, why don't we just use fast twitch muscles? Why have slow and medium twitch muscles? Again, note that the drawing uses red, pink, and white color to show that each bundle specializes in one speed type. The problem we face is how to get the energy we need from the food we eat to make the muscles work. Besides speed, which affects force and power, the three types differ in where they get their energy and how fast they fatigue. When a muscle fatigues, it cannot continue to compress. Slow muscles get their energy directly from the sugar and oxygen in the blood. They can fatigue, but this happens very slowly depending on the activity. Fast and medium muscles need to rest to rebuild their energy stores and clear out waste products created while they were working. Medium muscles get energy mostly from the blood, but they also have energy stored during rest. Fast muscles get their energy entirely from stores created during rest. They can sustain continuous work for only a few seconds before becoming completely fatigued. Normally, we use these fast muscles only briefly to give us the peak power we need for the hardest part of a task. Different muscle fibers have different jobs. Because they get their energy directly from the blood and fatigue so slowly, we use slow muscles for sustained activities such as breathing and standing and sitting up. Because they use a combination of blood and stored energy and can keep working for a relatively long time, we use medium muscles for higher tempo activities such as housework and walking. Because they can provide great power with their quick speed, they but only have tiny bits of stored energy and fatigue so quickly, we use fast muscles for the peak portions of tasks such as stepping up, getting out of a chair, and recovering from imbalance. Now say that again. Recovering from imbalance? If you have PN, don't bother trying to get preferred rate life insurance. The insurance companies don't expect you to live a long life. Why? Because PN patients fall, and falling is dangerous. So how do you recover if you trip, step on a crack or a stick? Mainly, you use your fast twitch muscles to make little momentary adjustments to your stance. Yeah, they poop out in a second or so. That fraction of a second can keep you upright. Lose them, and you can lose a lot. So, how do we make a muscle work harder? We have two techniques. First, we call on more bundles. Most muscles have lots of bundles. That allows the muscle to exert a wide range of force. Looking at the diagram, over a brief time, we try to exert more force, we call on more bundles, and we get more force. In the diagram, we show adding more bundles to the right of the diagram. Exactly how do we call on more bundles? Well, we'll get to that. Second, we call on faster bundles. We use the slower, least powerful ones first, and then add the faster and more forceful ones. In the diagram, we show this by the colors. First using the red ones on the left, then adding the faster medium bundles in pink, and finally the fast bundles in white on the right of the diagram. This is a kicker. So, we want to walk up some stairs, or we trip and we want to regain our balance. That requires force, strength. Momentary, yes, but without it, we cannot perform. On the left, we have the strength. On the right, look what happens when we lose those fast muscle bundles. Our muscles cannot provide the force we need. We poop out, we fail, and perhaps we fall. To repeat, almost every muscle is a mix of three types of bundles. The mix is important to generate the force we need to perform a task. There's a strong tendency for the mix to get slower when we age. Without PN, there's no specific age at which this process starts, but we usually see it to happen at some point if some sudden illness does not do us in first. Not many of us live to be 120. But with PN, this change becomes much too early. So when we hear the phrase, use it or lose it, what we mean here is use the full mix of the bundles or lose that balanced mix of bundles and with it the peak strength we need. How do we do that? That's where good personal trainers and gyms and all kinds of activities become our most important health activity. Why does PN make it worse? First, in the previous slide, I showed the little image of a downward trend to lose faster muscles, losing the runners and the jackrabbits. Why do we lose muscle bundles? And why do we lose the faster ones first? PN kills motor nerves. When the motor nerve dies, the muscle bundle dies. PN's not selective. It kills slow, medium, and fast motor nerves about the same. Slow muscles support us. They're essential to keep us alive. Faster muscles, on the other hand, keep us mobile. We can survive with less mobility. To preserve essential functions, the body will convert remaining faster bundles to slow ones. In other words, the body cannibalizes the faster muscles to keep the body alive. The result, the percentage of fast muscle goes down. We get weaker. Exercise slows loss of fast muscles. Why? First, remember the use or lose principle. We've all heard that phrase. The body has only so many resources. You'll spend those resources to defend the nerve cell you use. If you do not use a nerve cell, the body will be much less likely to defend that cell. The weakened nerve cell will die and take the corresponding muscle bundle with it. Remember this diagram we showed you earlier. We always use the slow muscle bundles first. We only use the fast bundles when we push hard. If we don't push, we may not use the fast bundles at all and lose them to PN or to the cannibals. Proper exercise fights this tendency. By proper, I mean a balanced combination of all types of exercise that pushes us to our peak. That is needed to build muscles. Few of us know what that combination looks like. That's what we need experts for. As PN progresses, the muscle cell may eventually die anyway, but exercise can buy us precious time to live without falling. Up to this point, we've discussed losing entire bundles of muscle fibers, but PN damage is not limited to just killing off bundles. It also damages how effectively we can use the bundles we have. That is, it damages our timing and that damages our strength. Let me show how. To start, let's revisit our twitch diagram and its movie with its moving red filaments to show how twitches can be used in sequence. This will let us show a bit later how our strength can be damaged by bad timing. Remember, the red filaments are the innermost parts in our Russian doll image of a muscle. These filaments are the parts that move to compress the muscle. Each twitch moves the filaments inward a tiny bit, but we rarely use a single twitch. We use them instead in sequence. Let me show you that sequence of two. First, one that compresses and then completely relaxes, and then another. Any muscle cell is capable of a sequence of twitches. It's those sequences that we use to control our movements. The twitch is a response to a nerve signal and takes a bit of time. But if it's not too fatigued, the muscle can start another twitch. Let me show you that little movement again. It's tiny. Note that because these twitches completely relax between each other, the amount of force generated is limited to that of a single twitch. To generate more force, the two twitches must be carefully timed. The second twitch must come before the first twitch has completely relaxed. Let me show you what that looks like. The first partially relaxes, but then the second one starts. We can see that the second twitch, by starting earlier than in the previous slide, causes the filaments to caress further inward, generating more force. More force, but with the same effort, the same expenditure of energy that we saw in the previous two twitch sequence. Let me show it again. It goes in, and then it keeps going in a little bit more. To achieve a maximum force from a single muscle fiber bundle, the motor nerve must send many twitch signals. The twitches must be carefully timed so that each arrives just in time to smoothly build on the previous twitch. When the muscle gets fatigued, the muscle will be unable to generate additional force. That is, peak force will have been achieved and will eventually need to relax, regardless of more arriving nerve signals. Let me show it to you. It goes in, and then in more, and then in more, and then more, and then more, and then finally reaches its peak, and then it has to relax. So, here's the punchline. What happens if our timing is bad? On the left, we see 4 signals that are timed to build force. Each signal comes before the previous one has fully relaxed. On the left, we see those same 4 signals, but there's a small delay in the start of the third signal. The second twitch has relaxed too much before the third arrived. The net result is no more peak force being exerted than we got with the first 2 signals. Yet the muscle had to exert just as much effort, wasted effort. Bad timing robs us of effective strength. It makes us weaker. PN interferes with the operation of our nerves. Bad timing creates weakness. So, where does this bad timing come from? Let me dig a little into the structure of the neuron or nerve, so the next set of slides will make some sense. First, a bit of an apology. Normally, a motor neuron controls a single muscle bundle inside a muscle belly, not an entire muscle. Hence, this illustration is not quite typical, but I'm using this illustration to talk about the neuron rather than the muscle, so I think it's okay for our purpose. The motor neuron gets chemical signals from other neurons. The arrow is pointing to another neuron. Usually lots of other neurons, not just one as shown in this illustration. The dendrites of the motor neuron receive these signals, and if there are enough signals from the other neurons, it will generate an electrical signal to send to the muscle. As you can see, there are lots of dendrites, the little sticky out things. There are lots of these dendrites. Why? Because there are usually lots of other neurons that it's receiving signals from. The dendrites of a leg or foot neuron are located inside the spinal column. The axon carries the impulse to the muscle. An axon can be quite long. Some of the legs and feet are 3 feet long. That length makes them especially vulnerable to the most common types of PN. The myelin, which I'll get to in a second, around the axon makes fast signaling possible, makes our timing possible. Finally, the junction of the neuron branches out within the muscle bundle to touch each of the muscle fibers being controlled. We mentioned the myelin around the neuron. The next slide talks a little about that. This little video illustrates the difference in speed that is gained by the myelin. The image on the left is without myelin and shows the electrical signal moving slower, perhaps so slow that the signal never gets to the bottom, never gets to the terminal, never gets to the muscle. The signal on the right is being successfully passed by a myelin-covered neuron. Damage the myelin, as some PN types do, and signal timing gets damaged. These motor nerves don't live alone. As shown at the beginning of the previous slide on neuron structure, motor neurons don't live alone. The motor nerves that drive our muscles are both interpreters and messengers. They process information from the body and then generate a message to the muscle. The message cannot be generated unless some signals come from the rest of our body. The data comes from the rest of our body. So, where does the data come from to control our balance and movement? First, of course, there is conscious control. We use eyesight, hearing, touch, and planning to decide to move and how. However, neuroscience has revealed that much of the time our brain has sent its movement signals to our muscles, even the ones we think we consciously decided on, before we realize we've decided to move. Habit and familiarity have a lot to do with so-called conscious movement. With PN, learning to be careful, learning to slow down and question our intentions becomes important. Most of our movement is not conscious. It's under the control of our unconscious. If you can still walk or ride a bike, you can only do that because your brain has learned to control those movements without you devoting conscious attention to how to contract those muscles. We once watched a man in a restaurant who had to consciously plan and coordinate every major step involved in eating, slowly reaching for a sandwich, gripping it, moving it toward his mouth, taking a bite, chewing, putting it down, living life in slow motion. Your brain and spinal cord integrate sensory signals from your eyes, hearing, inner ear, plus the nerves inner near the skin that sense damage, heat, and pressure. Additionally, you have proprioception sensors. These are sensory nerves in muscles, tendons, and joints that both give you information about your position and provide vital feedback as you move your muscles. The brain and spinal column must learn to coordinate this movement. Any mother struggling to hold on to a baby knows they are strong. A baby has strong muscles but cannot walk. It must learn to control those muscles. As PN removes or damages our nerves and muscles, we must continually relearn how to keep moving. This is an example of a proprioception nerve. A structure in a muscle called a spindle fiber has a sensory nerve that senses stretching of the muscle that is its length. This provides important feedback to the brain spinal cord, and in this case, directly to the motor neuron. In this example, the head says, lift the fork. The muscle contracts. The fork moves. The spindle senses tension in the muscle and can send feedback messages to the motor nerve and, not shown here, our brain nerves. For instance, if it feels a lot of stretch, the meaning is, hey, this fork is heavy, work harder. Or if it senses very little stretch, the meaning is, light fork, ease up, don't press so much. This feedback from your sensors is important to allow you to move accurately. Let's expand on the concept of sensory nerves from that last slide. Sensory nerves, such as the muscle, spindle, fiber nerve, are connected to multiple nerves in or near the spinal column. Here we show one sensory nerve, that's the one on the left there, that is connected to both the motor nerve and to a nerve going to the brain. The diagram only shows one nerve going to the brain, but in general, that sensory nerve will have terminal fibers connected to many nerves going to the brain. Those other brain nerves that aren't shown here are waiting to pick up signals from this sensory nerve and from other sensory nerves. The other sensory nerves aren't shown. It is the combination of signals from many sensory nerves that is important to the brain. When the sensory nerve sends a signal, note the little red arrows, that signal is detected by those two nerves and all the others that are not shown here. What is the result of this sensory nerve activity? The motor nerve in our little example controls the movement. That is, that it controls the twitches of a muscle fiber bundle. It must decide whether to fire or not. It makes this choice based on the number and kind of chemical signals it gets from the other nerves it connects to. In this simplified case, there are two input nerves, one from the sensory nerve and one from the brain, and the motor nerve will fire only if it gets a signal from both. We see here in this case that the motor nerve is only getting a signal from the sensory nerve, not from the brain nerve. Hence, the only signal the motor nerve sends with only one signal, the motor nerve will not send a twitch signal to the muscle bundle. Now, suppose the brain, in its infinite wisdom and experience and using any other sensory inputs it has, decides to fire the output neuron from the brain. When the motor neuron has the two inputs it needs, it generates a twitch signal to the muscle. In other words, your brain has a vote. With PN, your brain must learn when to vote. Here are the takeaways again. To review the connection between PN and exercise. First, we need to preserve or build the muscles needed for balance. When our nerves die, the muscle cells die. Our muscles are composed of types. The slower, weaker ones are essential to life. When those essential slow ones die, the body will compensate by converting some remaining faster, stronger ones into the slower, weaker ones, just to keep us alive. That conversion weakens us. Exercise pushes the body to preserve the faster, stronger ones. It's use or lose. Second, as we lose sensory nerves, we rob the brain of the signals it uses to control our muscles. The brain can compensate for this loss of information up to a point. Then its timing gets degraded, and as we saw, timing is a key element in getting strength from our muscles. Our brain needs time to learn how to deal with this loss of sensory inputs. Exercise gives brain the opportunities it needs to learn. That's basically the end of this presentation. I do want to go and add some editorial comments. Indulge me for a moment to allow me to give my basic editorial rant about the horrible state of healthcare with respect to PN. A presentation like this is necessary because of systematic problems with our country's approach to PN. We have educated our doctors to believe PN is a hopeless disease. Why diagnose it when you cannot do anything about it? We have watched our society's waistlines balloon and type 2 diabetes explode, but have not devoted the resources or standards to ensure that PN is screened and identified as early as possible. Tests for PN and concern for its metabolic precursors are not part of the standard examination doctors is expected to perform on middle-aged patients. Most primary care doctors have not been trained to use the best manual screening tests for PN. There are well-tested automatic tools for early detection that are being ignored by insurance companies. We have educated our doctors to believe that all pain is acute and directly related to ongoing tissue damage. We do not train our doctors in proper ways to handle chronic pain. We do not train our doctors to look for sources of pain that are not due to tissue damage. Scientists do not actually know much about what is going on in our peripheral nerves, especially the sensory nerves. Scientists have been studying motor nerves since Shelley wrote Frankenstein. Unlike motor nerves, the sensory nerves are almost impossible to study in humans. Even studying them in rats is extremely difficult and costly. Our best model is transparent fish with limited applicability to humans. Pain, on the other hand, is a mental construct our brains make to deal with both tissue damage and emotional stress. We do not yet have good model creatures that represents both the physical and emotional content of neurological damage. Rats are like us in many ways. Even their emotions can be studied. But we are a long way from having a rat that walks on two legs, overindulges in bad food, and exhibits a wide range of human ambitions and emotions. Even if we did, we probably could not withstand the emotional cost of experimenting with them. Hence, we have limited understanding of the mechanisms that work with PN pain. In any case, such pain is always chronic. None of our medications or treatments consistently yield pain relief, that is, much beyond placebo. And society builds in us expectations that the doctor should do something immediately. Hence, many patients and their helpless doctors are often caught in an endless cycle of try this and try that, rather than recognizing that PN's chronic nature and then adapting to it, or looking at the emotional underpinnings of that pain. Most tragic of all, when PN is finally diagnosed, our doctors do not emphasize the substance of this presentation. They do not tell us to get thyself to the gym, get ready for the oncoming train, and work hard to keep the physical ability to walk and chew gum. Diagnosed early or late, treating pain with exercise has its best chance if started as early as possible. With me, there was a 13-year delay. The train is coming.